Okay, thanks very much. Of my other two co-authors, Katie is here, and I hope we'll field some of the flak that comes at the end or maybe during the talk. Okay, so I'm going to talk about a quite different approach to the actual linkage process, to the things that are so far being discussed in this workshop. And before I sort of come on to that, I want to go very quickly through what I think is more or less the current state of the art. I won't dwell on this because that's very familiar to all of you, the question of using probabilistic record linkage to derive a set of weights which indicate where you are somewhere on a continuum between being a non-match and a match in terms of identifiers and the errors associated with identifiers. So I'm going to talk about what I call a file of interest and a linking data file. A file of interest is, if you like, my primary file, and I'm trying to bring across information from a secondary file. So quite a simple setup. And this slide simply runs through the traditional Felighi-Sunter type model. And again, I'm not going to dwell on this, as it's not particularly what I want to talk about, but simply just to introduce the standard ideas of the M and U probabilities, and the idea that we finish up with a classifier, which is usually this log ratio of the M and the U probabilities based on estimates that are derived from, well, essentially is a latent class model with two classes, matched and non-matched, and writing down something called a likelihood, which I put in quotes. So I'll come back to that on the next slide, and using things like the EM algorithm and so on to get the estimates. And then with these weights, these are weights in our own procedure, our PII procedure. We use those in the sense of we pretend they're probabilities, and we use them in a subsequent Bayesian modeling framework to do some imputation and fit models. So that's the standard framework. And whoops, going the wrong way. But there are some problems. And the first problem, and I'm not the only one to point this out, that in fact that model, that two-class latent class model, and the likelihood written down for that is not a true likelihood. And many people have pointed this out, Tancredo and Liceo particularly have done so, but there's a previous literature as well, and there's several reasons for this, but essentially you can think of this in the following way. You've got your file of interest, and given an observed pattern that you observe with a set of records, candidate records for matches, if you like, from your secondary data file. If you know that one of those is the true match, then by definition, if there is only a unique set of matches in your two files, all the rest are non-matches. And so there is a dependency here, and so the so-called likelihood we've written down is not a true likelihood because that assumes independence between the pairwise sets of observations. The Bayesian, there's a whole alternative literature that avoids that particular issue. However, this is not a criticism of the Bayesian literature. I think the Bayesian literature is interesting. It goes beyond what we already have, but it too, of course, makes many assumptions in order to get identifiability of parameters. And this is just 3 bullet points about the original Tancredo and Liceo model. I don't want to dwell on that again. It's not a criticism of that. I just want to point out that existing procedures are all making assumptions, and indeed I'm going to be making some assumptions as well. But what I think all this amounts to is that the traditional models, the models we have, can be regarded, certainly the traditional Felighi-Sunter type models, essentially giving us a convenient algorithm to maximize a certain criterion. It's written down as if it was the likelihood, but and to give us some final weights or classifier that we can then use. And indeed, this is a useful thing to do. It's a sensible thing to do. We know, both empirically and also theoretically, that it's an intuitively sensible thing to do. It gives us results that make sense. So what I'm going to suggest is an alternative, and I think also intuitively appealing procedure that will do the same kind of thing. And the reason I'm putting this forward is on the grounds that what we have at the moment actually should be viewed as a computationally convenient algorithm that has certain intuitively appealing properties. And I want to suggest that these are not the only set of algorithms, there are different ways of looking at this, and there are certain advantages in the particular set of procedures that I'm going to demonstrate. So just to kind of set this up, assuming we've got P identifiers, and each of the identifier has several ordered states. So in the simple case, it's just 0, 1, agree, not agree, but maybe degrees of agreement, and I'm going to allow that level of generality. So that's really what that says, and n is the total number of categories overall. So I'm going to give you an example with 4 identifiers. They're just 0, 1, match, non-match, agree, not agree for each pair, and so there are 4 times 2, that's 8. N is thus 8. So n is quite small, and in general, and this is one of the claims that to utility that I'm making, is that n is never too large. It's within the bounds of computational facilities that we have available. So that's setting it up. And now what I'm going to do for each of the categories, I'm going to assign a score. I'll come on to how I do that in a minute. And this score for each of the categories is meant to represent for each individual, so it's either 0 or 1 in this case, this is going to be a reflection of an underlying scale which goes from 0 to 100, say, we can fix the endpoints, which measures at one end complete non-matching. Okay, so these are the non-matches. At the other end, when you get a final score of 100, these are the complete matches, and in between, on the basis of the information we have from the identifiers, we have an intermediate score. So if you like, a propensity to be a match or a non-match. So it's a scaling procedure, and the aim is to try and put every single pair, which is not a sort of complete match or complete non-match, somewhere on that scale, and that's going to be the equivalent of our R statistic that we had before. So let's assume we have these scores. So each of the zeros for each identifier has a score X. For pair, and for pair I, the sum of those is going to be a classifier, okay? And Zij is equal to Xij, where the pair I has state K for identifier J, okay, with Kj categories for that identifier. So Z is the score for pair I, okay, or the weight, if you like. And I've already said this, we've got 2 classes, so Z is going to vary between 2 fixed endpoints which we're at liberty to fix, and I'm going to suggest that we have 0 and 100 for convenience. And these endpoint constraints in my system are of course essential, because it's those that provide identifiability in a non-trivial solution, which is described, hopefully, on the next slide. So this is how I do my estimation. So I'm going to form a discrepancy, if you like, a loss function, which is, for each individual, I've got my Zi, which is a sum over the weights assigned to the categories, and the sum of squares for that individual, for each of the Zij, for each of the separate weights, for each of the separate identifiers, minus Zi, that is the within pair squared discrepancy, and we're going to add those up over all possible pairs. So that's my total loss function, my total discrepancy, and I'm going to minimize that. And the reason, the intuitive reason for minimizing that is that each of these x's, right, so any given individual is meant to represent the position on this underlying propensity scale. So minimizing it is an intuitive, obvious thing to do because that's what these are meant to be, because you're averaging them up, or summing them, or averaging them to give your score for that individual. And so what we do is we minimize this big D subject to those endpoint constraints. There's a couple of vectors there that give you those constraints at 0 and 1. And it turns out that that, in fact, is a very trivial numerical problem. Essentially, it's a standard numerical algorithm. You're solving a set of non-homogeneous linear equations. That is totally trivial. Any self-respecting computer system, you can do that with a couple of commands. No problem. It's fast. The storage is n by n. Remember I said n is small. It could even be 300 or 400 if you really sort of work out nim. That's no problem. 300 by 300 matrices could be stored easily. And the only computing, I'm not going into the details of how you solve that. You have to set up some matrices, but essentially those matrices of order n by n, there's just 2 or 3 of them, are simply set up by counting. You just run through all possible pairs, counting agreements, non-agreements, or in between if you've got more than 2 ordered categories. You don't need to block. Storage is not a problem. You can handle vast data sets because all you're doing is just running them through. You're just reading them, running through memory, and just counting. It's extremely rapid. You can also introduce identifier weights. So instead of simply summing these discrepancies, the Zij minus Zij, you can actually weight them for each identifier. So you may think that some identifiers are more reliable than others. You might want to give them more weight in determining this, the weights going into the function. And so you can introduce a priori weights, Wj. That's not a problem. That just all runs through. It doesn't add any kind of complexity to what you're doing. It also handles missingness quite nicely. If identifier is missing, you can retain consistency of your estimates by randomly sampling. For example, if it's missing completely at random, you just randomly sample from the distribution you happen to have. But it may be missing at random, conditional on other things that you happen to have available, which may be other identifiers, but they could be attribute data in the files. So you can then sample conditionally on that set of variables if you want. So in principle, at least, missing data, missing identifier data, shouldn't actually be a problem. So now I'm going to go through it. How am I doing, Natalie? I'm doing okay, good. So these are synthetic data. Thanks to Katie, they're actually data that we used in our 2012 paper, and Katie's kind of played around with them. So we've got some relatively small files. The file of interest is 7,800 records. We've got a linking data file of 10,000, unique matching, and the M probabilities for each identifier are fixed independently at 0.95. They're not exactly 0.95, but they're generated, the data set's generated to give you that, just to make comparisons easy. And what we've done is the first row there is what comes out of our scaling procedure. The second row is what comes out of a traditional PRL algorithm, but fixing the MJ, 0.95. So we're not running into any kind of estimation problems. And what you can see, of course, we're getting different. These are the standard R weights we get, and of course we're getting different results from our scaling estimates. You'll notice they're in the same order. So the order is the identifiers are day, month, year, and sex. And these are the weights for when you get agreement. So when you've got a pair on an identifier that actually agrees. Okay, so you score a 1. It turns out you can make all the disagreement ones, rather than making the sum of them equal to 0, you can, it's a trivial rescaling, you can force them all to be 0, which is quite convenient. So when they don't agree, they're 0. So these are the weights when they agree. And they've got different relative importance. But they're all sensible. So the most discriminating one is day, because you have 31 possible days. Okay, month, you only have 12 months. Year, I think in this case it's 6 years, was it? Okay, I can't remember exactly. And sex, obviously, just have 2. So they come out in the right order. Both methods give the right order, and that's fine. I think it's worth noting that the PRL weights, the weights we usually compute, the log to base something or other, 2 usually, m over u, that scale's arbitrary. That's an arbitrary classification. You can do a monotonic transformation of that. Doesn't matter if you're just interested in thresholds. That's fine. It's absolutely trivial. You're not making any difference. So you want to convert them to probabilities in a kind of pseudo-probabilistic way. Then the scaling does matter if it's non-linear. But essentially, what most people do, the actual scale doesn't matter. As long as you have a monotonic transformation, you're fine. And in fact, it turns out you can do the sums. If you take the PRL estimates and you exponentiate them, in other words, then you work on a log scale, you work on the m over u scale, they're very close indeed to what we get for scaling estimates. So the next slide actually shows what you get for each linkage pattern. So now both of these methods have assumed independence, so we're just adding up across identifiers, adding up the logs, for example. We get pretty good agreement, certainly at the ends, it's exact. So for the traditional method and the scaling method, the linkage pattern 0, 0, 0 is identified correctly, as is the final one, and also the ones near that. There's some wobbling around in the middle, which is what you might expect, because there's an arbitrariness here. We're making some assumptions, traditional PRLs making some somewhat different assumptions, so you expect some variation, but this is reasonably encouraging, I think. I'm nearly through. Fantastic. Okay, just to summarize, if we have a continuous, like a sort of sound-Xing agreement measure, then we can discretize this, to pull it into the same framework. It is possible to run this method with a mixture of discrete and continuous. We would need to change our software a little bit, but you can solve the equations. It's just a little messier, actually. So it's probably convenient to discretize things. We're not, strictly speaking, subject to the independence assumption. It doesn't enter into what we're doing. But what we can do very easily is we can combine identifiers. So if you have 2 identifiers for categories, we can form a combined 4-category identifier if we think that that's actually going to give us more sensitive classification. We can do it for sets of 3 or more as well. So there's a lot of kind of playing around with combinations of identifiers that you can do, and that introduces no new complexities. In fact, it simplifies certain things. Although this is not a based on a probabilistic model, or as I prefer to call it, a pseudo-probabilistic model, as in Filigi-Sunter, you can still introduce the probabilistic notions by thinking of the data sets as being sampled from some universe or superpopulation, and then you can get things like interval estimates via bootstrapping the pairs and so on. So you can have all that if you want it. Missing identifiers can also be handled. I won't dwell on this last one, which is really a separate thing, but it's to do with partly what Katie was talking about, the training data. The same issue about lack of independence actually applies to when using training data, semi-unstructured PRLs But I don't want to kind of dwell on that. I really want to kind of put this forward as a quite different approach that I think has some very practical advantages, particularly in computability and convergence. This always converges. Never have a convergence problem because it's deterministic. You're just solving a linear equation, as opposed to, I think, a lot of people's experience with things like EM algorithms, which maybe depending on where you're starting, types of data you've got, can have convergence problems converging to the wrong maximum, local maximum, or not converging at all. Certainly we've had those problems. So I think I'll stop there and open up for general discussion.
Yes, please.
Hello. I think this was very interesting. Thank you. I just wanted to ask if is there a paper about this that we can...
The paper's been submitted for publication. Some of you may well be refereeing it at the moment. Please. Katie, do you think we could make it available? It has been submitted, so yeah, would you like to email me or Katie, and we can send you the comments, obviously, welcome.
Another question, maybe. You said about using continuous variables, the system can be adapted.
Yeah.
But I thought, my intuition was, since you are solving linear equations, continuous variables would be even easier than discrete variables. Is that not the case?
They're no more difficult, certainly. I mean, I don't possibly easier, but no, they're no more difficult. You can fit them in. It just happens that at the moment the software we've written to do this doesn't actually allow you to put. But it's a relatively trivial change. But you could put it in, yeah.
I guess I can ask more detailed questions later, but do you not use something like Gaussian elimination?
Yeah, yeah, but we do. In fact, actually there is another slide. The software is written in MATLAB, and we use MATLAB routines to do the core estimation. Yeah.
Hi. So it's very interesting, and I think there's a lot of overlap with the presentation that I'm going to give tomorrow. So that's going to be interesting.
Oh, well, good.
But so I was curious for the minimization. Like, to solve the equations, do you enforce the one-to-one assignment restriction, or do you? It wasn't clear how you handle that.
We said the one-to-one.
Right. So I'm assuming that you're like the files that you are thinking of. They have you have two files,
yeah.
And you are assuming that they don't have duplicates within.
Yeah. In this example, yes, that's right. So, but we can extend it to include duplicates as well. Right. But we need then to sort of make some decisions about how you're going to deal with those. You're going to kind of use some kind of weighting across them or whatever. But yeah, this is assuming it's one-to-one. This
and
at
so
the moment, yeah.
In the minimization, so you have the sum of the discrepancies.
Yeah.
I don't remember the formula. Right. Yeah. So in the minimization of that problem, do you enforce the one-to-one assignment, or like for the implementations that you?
By the time you get to this, you haven't got this is just a straightforward minimization. Yeah.
But you don't, because you could minimize the same objective function, enforcing the one-to-one assignment. You could solve it in a straightforward way without ensuring that you will end up having a one-to-one assignment. But then I don't know how you solve it.
Well, you can't sort of just minimize this function, because otherwise the minimum is 0. There's a trivial solution, which is that all the scores are 0. So you've got to impose some constraints. Now, you can impose whatever constraints you like. You could say that one of the weights is 20, another is 40, and you get a solution out. The point about these constraints is that they're the natural constraints, that when everything disagrees, you're a non-match, and when everything agrees, you're a match. Okay, so they're natural constraints. You don't need more than 2 constraints, so there's no need to put any additional extra information into that minimization. I'm not sure I totally picked up your point, but
Well, I'm just not sure how you end up ensuring that the linkages that you at the end the linkage decisions that you take are one-to-one, maximum one-to-one. We can talk about that later, but it's just that
You get possible pairs
yeah,
of
no,
high weights as
you
well.
I mean, not necessarily. No. You're not guaranteeing that. All you're saying is all you're doing is identifying each identifier pattern somewhere along the continuum from 0 to 100. That's all I'm doing.
I see.
Okay? I'm not making any particular other assumptions about how many links there are. Okay? That's all I'm doing. Now, I could. It would be possible to those weights I've introduced to the identifier. So that was, where was that? Okay, down here. Okay, I can also introduce weights associated with particular x's, particular scores, if I wanted to. But that's generally I wouldn't see any particular need to do that. But no, there's nothing that says this is one-to-one or not one-to-one in the procedure. No, there's nothing in there.
Can I follow that up then? So if it's not one-to-one, if you're deduplicating any number of databases that may or may not contain duplicates, and you have a whole series of pairs which refer to the same underlying records that have just same or similar scores, do you have a clustering step then that decides how those fit together, or how do you decide which records are co-referent?
Okay, I mean that'd be a separate thing to do. I mean, yeah, you may want to deduplicate before you go into this, as you would normally want to do with datasets. So any of those kind of issues are to do with the data. But what we're assuming is you've got a data set and you're making the assumption that there are just one-to-one matches already. So if there aren't, you need to do something about it, clearly. But there's nothing actually built into this procedure itself. This is simply a procedure that is an alternative to the traditional so-called likelihood-based procedure for deriving weights. Okay, that's all we're putting forward an alternative to that. We're not trying to kind of generalize, say this can handle duplicate records and all the rest of it. Okay, so I
Clearly, if you had duplicates and you used that method, they would all be high matches, and you would select a number.
Yeah, that's right. I mean, yeah, it's not.
You could do that, and then you could apply clustering in the same way that you would use the weights from any other classifier.
Absolutely, yeah. You could use all those techniques, post or pre, to deal with what you get out of this. So it's not specifically designed to deal with those. It's designed to replace a particular step in what people do.
I gather that weights are estimated without training data in general, and so I can see where the weights are coming from by minimizing the sum of squares. But in terms of the intuition, is there some reason that those weights translate into a good classifier? Does it have any kind of properties in the sense of giving you the best classifier within some family of classifiers?
No, this is a class of scaling methods. It's a subset. It's a special case of what's called correspondence analysis, for those that may come across. Correspondence analysis is usually not done in quite the same way. It uses different constraints. It uses a kind of mean and variance constraint. But essentially, it is an example of correspondence analysis, which is not a probabilistic model of any kind. So all you're doing is you're setting up a loss function and you're minimizing it, okay, subject to some constraints that you have to impose for identifiability purposes. So what you're doing is you're saying, well, I think this is a sensible loss function, okay? Do I use a squared loss function? Do I use an absolute deviation loss function? You have a choice. You always have a choice. You have a choice in regression analysis. You can use mean deviation regression or standard least squares regression. You get different answers. What do you use? Well, you've got to make some judgment about it. But you've got to make some assumptions about the loss function procedure you're going to use, and that's a sensible one. And what I'm saying is we're it is a sensible one. If you believe that these scores are all reflecting the same underlying position on the scale, then that's a sensible loss function to use. I could minimize the sum of fourth powers if I wanted to, but it's convenient to minimize the sum of squares for a whole lot of reasons. And I'm imposing those, what I call endpoint constraints, because they seem natural ones to impose, where you've got a scale that runs, that were basically the two classes, and you're somewhere between them. So I'm appealing to what we know about the problem to justify the particular mathematics here.
Will you kind of get back to Legge-Sunter if all the data kind of satisfy conditional independence?
Yeah. Well, it doesn't actually come into this. It's not a probability model. So you don't have the notion of conditional independence, which is something to do with probabilities. So you only have the notion of conditional independence if you're writing down probability distributions. Okay. It doesn't actually occur. This is a scaling procedure. The notion of conditional independence doesn't exist. But what I did say was that you're considering separately the identifiers. So if you like, that's the analogy, but you can put the identifiers together, right? If you think the weights don't add linearly, you can incorporate interactions, which is what I'm doing by saying if I've got two identifiers, I can form a combined 4-category identifier. So that's like putting an interaction into an additive model. Okay, so that's how I would elaborate it. That's the analogy.
I'm just thinking, although you didn't come at this from a kind of a probabilistic approach, you could kind of still subject it to kind of a probabilistic analysis, or if your pairs are coming either from some kind of data generating process or sampling from a large population, then the weights are going to converge to something. And
that's absolutely right. And that's why I said you can think of a kind of superpopulation that you're sampling from, if you want to. Or it may be you want to divide your data into subgroups, subpopulations, if you like. So you can do all of that. You could impose all of that on top of this and still run this. So yes, you can have some kind of sampling kind of theory associated with it.
Chris?
Yeah, could I just ask about that sort of inference based on the superpopulation you talked about at the end? I mean, you're talking about bootstrap methods, and I thought you were suggesting that these would not be subject to the kind of dependence issue you raised at the beginning, but I wondered if the structure of the different pairs doesn't impose some kind of dependence that would make your bootstrap inference question more.
No, I don't think so, because all you're doing is you're just estimating these weights, these scores, using an algorithm, and so all you're doing, if you think of sampling and using a bootstrap to kind of mimic repeated sampling from superpopulation, you're just generating a distribution for those functions in that estimation process. So it's deterministic, so that if you like, each time you generate bootstrap, you fit the model derived set of scores. That's purely deterministic, so it has all the usual bootstrapping properties, and you don't need to invoke independence or anything. As long as you're happy with bootstrapping, repeated sampling with replacement, then I don't think you need to worry about anything else. I think it has the right properties.
We can just jump in. But so when you mention bootstrap, are you thinking of bootstrapping the pairwise scores, or would you bootstrap the individuals in the original?
I'm thinking of bootstrapping the pairs actually.
But in that case, then they are indeed dependent, right? I mean.
Oh yeah, absolutely. They're dependent in the sense that I specified, but the procedure doesn't recognize that. Okay. If you, instead of thinking about bootstrapping, thinking about a superpopulation and randomly generating pairs of files, okay, in the same way, and these are quite different. Now these are quite different sets of pairs, okay, and all I'm doing is just I'm forming a statistic based on minimizing this loss function, and I'm just looking at the distribution of that statistic over repeated samples. That's all I'm sorry I got into this, because that's a kind of, it's not in practice something I think many people would want to do. I was simply pointing out that if you wanted to do that, you could do that. And you don't need to just do it with this method. You can do it with any method, if you like. It's just repeated sampling from some superpopulation to get the characteristics of the statistic that you're deriving from the sample. And you can mimic that with resampling bootstrap in a simple case. That's all I'm saying. But you may be right that it's not realistic to think of sampling pairs in the same way from some superpopulation. You may want to do it some other way. You may want to kind of sample your file, what I call file of interest, and then in some way sample a set of other files, and doing that repeatedly. There are different ways of kind of doing it. The simplest way is to sort of think of sampling pairs, because that's relatively straightforward. But you can do it in other ways. You can set up different sampling schemes.
Okay, I think we need to close the discussion. We'll take it offline during coffee. Thank you very much.